Hi guys, it's your science teacher here, back with another video, and this time I'm going to go through all of the properties around electromagnetism and magnetism. We are going to look at how we can induce a current using magnets, also how we can create magnets with electricity, and look at some differences between permanent magnets and induced magnets. So sit back, relax, and enjoy this video. Let's start off today's video by looking at magnetism, what it actually is, and some examples of some permanent magnets. So here I've drawn the standard bar magnet, and you probably know that a bar magnet is a permanent magnet, and your teacher probably showed you it by showing its magnetic field lines. And all permanent magnets have this property that they produce a magnetic field all the time that cannot be turned off. So if we draw the field lines on this bar magnet, they go out of the North Pole and they go around and in to the South Pole. And they actually spread out. The further away you get from the poles, the weaker the magnet is. Now, permanent magnets will induce a force onto some magnetic materials, and there are three magnetic elements that you need to know about, and the three magnetic elements are copper, iron, and nickel. And it's quite easy to remember the three because they're all next to each other in the periodic table. Now, these three magnetic elements do not need to be pure in order for a material to be magnetic. For example, some steel materials are magnetic because iron is a primary component of steel. Now, paper clips are an example of one of these magnetic elements. It's iron that's inside paper clips. In fact, paper clips are an alloy of steel, and if I put a paperclip in this magnetic field, it will be attracted to my magnet. And we're going to look at our first property of magnetic materials now, and it's a property called induced magnetism. Now this paperclip is in contact with this magnetic field and touching this magnet, it now in fact turns itself into a magnet. That's why it's called induced magnetism. And its poles line up exactly opposite to the magnet itself. And this paperclip could in fact pick up more paperclips along the way, and then that would have opposite poles to itself. And as you get further away from the magnet and the magnetic field lines spread out, the weaker the effect of the induced magnetism is. And as soon as you take these paperclips away from that magnet, the induced magnetism is gone. An example of a permanent magnet that you all know is the Earth. And the reason why the Earth is a magnet is because of the fact that it has a mantle layer which is liquid iron, which is in constant motion around, and that causes a magnetic field to be produced. And compasses, even the one inside your phone, they line up to magnetic north of the Earth and magnetic south. And the magnetic poles on the Earth are not exactly perfectly north and perfectly south. In fact, the difference is around 3 degrees worth of difference that you get by using magnetic north and magnetic south. And travellers who do use compasses do take off them degrees in order to account for the difference. Now, if you have two oppositely poled magnets and you put them facing each other, what will happen is they will attract one another. And all that happens is the field lines line up, still going from north to south, and you can see that attraction going on. This could be the other way around. I could put the south on this side and the north on this side. However, in this example, I did not do that. But then the rest of the field lines all look the same going around. The only difference is those attraction lines that you can see there. However, what happens when you've got two like poles and you put them facing one another? You see a property called repulsion, and this is where they do not want to be in contact with each other and they will bend around. The way I like to remember it is opposites attract, and therefore when you've got two likes, they do not attract, they repel each other and they bend around each other to make sure they do not come in contact with one another. And just like the top one, it would work if it was the other way around. So if I had both norths this end and both souths this end, you would still see this property called repulsion. Now, these permanent magnets will always show this property of attraction or repulsion with their poles, unless subject to really high temperatures, in which case they can, in certain cases, become demagnetized. But you do not need to know about that. If you want to be able to turn your magnet off and on, rather than demagnetize it in order to turn it off and on, you need to create yourself an electromagnet. And the way it works is when you have current running through a wire, it creates a magnetic field, and if you wrap it round a magnetic object, you can create yourself a magnet itself. And the cool thing with electromagnets, and the reason why they are more beneficial than using permanent magnets, is because you can increase and decrease the strength of that magnet. You can do that by changing the amount of coils. The more coils, the bigger the strength of the electromagnet. Also, you can increase the strength of the electromagnet by increasing the current going through it. Or even you could change the strength of the electromagnet by changing the material. Also, the real benefit of using an electromagnet is the fact that you can turn an electromagnet on and off when you need it. This school bell up here shows an electromagnet and how we can use electromagnets. When the switch is closed, as it is here, then a current flows through the electromagnet. This causes the metal arm to be activated and it will hit the gong, making a ringing sound which you hear in your class to signal the end of the lesson. You may be happy about that or not so happy, depending on which lesson you have. And once it hits the gong, that's when the electromagnet turns off, because the circuit is completed again and it will return to its position. The electromagnet will obviously turn off again when this switch opens, and that will turn off that electromagnet. We can investigate the strength of an electromagnet using paper clips, and that's probably what you did at school. You probably changed the amount of coils around your electromagnet and saw how many paper clips it could pick up. The more paper clips, obviously, the stronger the electromagnet. You can also change the current and see whether that affects the strength of your electromagnet as well, and you may have done that one in school as well. We're now going to look at one of the most important properties of magnetism, and we're going to look at something called the motor effect. The motor effect is used in nearly every appliance now, from electric cars to even hair dryers and CD players. And the motor effect uses that same principle that we looked at in electromagnetism, that a current carrying wire creates a magnetic field around itself. Now we have to use something called Fleming's left-hand rule to look at how the current carrying wire actually creates a spinning and motor effect inside a permanent magnetic field. So over here I have an example of a motor. This here is the motor that we are going to look at, and we are going to apply Fleming's left-hand rule to find out which way it spins. The first thing I like to do is look at the charges on my current source here. So it says that it's negative here and positive here, and electrical current flows from the negative terminal into the positive terminal. So that is the direction of my current. Next thing I do is I look at where my magnetic field is going from and to. And we know that magnetic field lines go from the North Pole to the South Pole, so let's draw them in as well. So I have my magnetic field lines here. Remember, magnetic field lines are invisible. I'm just using this purple line to illustrate where they would be. Now, if we look at Fleming's left-hand rule, each finger here has a label to it. We have our thumb showing the force. This is the direction that the coil will move. We have here the index finger, or the pointy finger, which is known as the magnetic field. And here we have current, which is the middle finger, or sometimes students call it the flipping off finger, which is that middle finger. And the way we use Fleming's left-hand rule to work out the force is that you're going to have to put your left hand on to the screen. Now, what I want you to do is, if you can do this, this will be really cool. I want you to put your left hand actually on the screen as you are watching this video, and I want you to point your index finger going from the north to the south, because that is the direction of the magnetic field. Then what I want you to do is I want you to rotate your hand in order to make sure that the current is going in the same direction as this blue arrow is as well. Once you have done that, you will notice that your thumb is pointing into the screen. And this is the turning effect at this point here. It's going into the screen. What's happening at the other arrow? Well, the magnetic field is going exactly the same direction, still north to south. So put your hands back on that screen again and keep your pointy finger pointing north to south. This time, though, your index finger, your middle finger, will be pointing towards yourself. Okay, it'll be pointing towards yourself because the current is going in the opposite direction. And what you should find this time is your thumb is pointing out of the screen. This is causing a turning force upwards. And as you can see, the two turning forces are going in opposite directions, and this causes the spinning effect that you see inside of a motor. Now, you might be saying, what happens when it gets halfway round, though, and then it's still it will feel the force in the opposite direction, and it would just keep flicking back and forth? Well, that's where this thing underneath comes in, which is called a split ring commutator, and this basically alternates the current every time it gets halfway around that loop. Without the split ring commutator, it would just keep flicking back and forth from its original position to halfway round. So using the split ring commutator, it creates an alternating current, and therefore you can keep finishing your loops and it will keep turning in the motor. If you are doing combined science, well done. You have absolutely smashed it. You are finished for this video. If you are doing triple science, just a little bit longer to go. So we've learned about the fact that when we put a current through a wire, we create a magnetic field. And when scientists discovered this, they were really, really excited because they wanted to see if the opposite could be observed. And whether we could use a magnetic field to induce a current. And that's what we're going to look at now, called the generator effect. I can actually see the amount of current and voltage that I can create by using the generator effect by making this simple circuit. Now, all I have is a coil of wire connected to an ammeter and a voltmeter. And in order to create a potential difference in the circuit, what I need to do is I need to change the magnetic force that this wire feels. And to do that simply, I just need to move it up and down in this circuit. If I move it down and into the magnetic field, it will experience a changing magnetic field if it's moving, and therefore a current is produced. Now I can actually reverse the direction of the current and the potential difference by moving it the other way. But an important thing to remember is if it stays constant and it is not moving, then there is no changing magnetic field and there is no current or voltage produced inside that circuit. So the key to electromagnetic induction is the fact you need a changing magnetic field. I can also alter the strength of the current and voltage produced. The way I could do that is by turning my circuit into a coil, and the more coils, the greater the potential difference. Also, I can increase the strength of my magnets, or I can increase the speed that I move my circuit through the magnetic field. Because we know that changing the direction of the magnetic fields can induce a current, you could do it the opposite way round as well by inserting a magnet into a coil of wire. If you insert the magnet and keep it moving, you are changing the magnetic field and a current will be induced. Now you can reverse the direction of that current by just changing the poles of the magnets around, and that will reverse the direction of the current inside that circuit. Generators are in fact what we use in order to create our mains electricity supply. Here we have an AC generator. And because of the fact you have a changing direction of currents, it produces alternating current from a generator like this. And this is what we get in our mains frequency supply. It actually flips the current backward and forth at a speed of 50 Hertz. So we are so nearly at the end. We are going to look at one last property of electromagnetism, and we are going to look at transformers. Not the cool iron robots, no. We are going to look at the transformers we use in order to step up or step down voltage. Now you might say, what does this mean? Well, step up voltage, it's in the name a little bit, but step up voltage increases the voltage, and we have step down transformers as well, and they decrease the voltage. You might also be thinking, where in life would you want to step up or step down the voltage? Well, it's very important because you need to increase the voltage before sending it across on long distances. So along power lines, for example, they increase the voltage to incredibly high numbers because this means that there is less resistance, so less energy is lost than was created. And step down transformers are used to make the electricity safe to be used in houses. When looking at transformers and how transformers work, you might have to watch this video a couple of times about the transformers because there's some key terms we need to use in order to get the marks in an exam. What you have here is you have a primary coil and you have a secondary coil over here. And you have an iron core. The first step in creating a transformer is you have an alternating potential difference attached to the primary coil, and this creates an alternating current amongst the primary coil. And as you've probably guessed, an alternating current does produce an alternating magnetic field in that primary coil. Now, because iron is a magnetic material, this will create an alternating field in the iron core as well. And the last step is that it produces an alternating potential difference in the secondary coil. Which, if it is in a complete circuit, which it most likely is, that will mean that you have a current flowing as well. Now, you might have noticed in this transformer that I've drawn here, I have 4 turns here in my primary core, and I have 8 turns in my secondary core, which is twice as many. So if the voltage here was 10 volts, that would mean the voltage in my secondary coil would be stepped up to 20 volts, as I've just doubled the amount of coils. But there is an equation you can use if you don't have such simple numbers to work with. You have voltage of the primary core divided by the voltage of the secondary core equals the number of coils in the primary core divided by the number of coils in the secondary coil. So if you were wanting to calculate the voltage in the primary, if you know the voltage in the secondary, what you could do is you could do the voltage in the secondary times by the number of coils in the primary divided by the number of coils in the secondary. I hope you've enjoyed this video. I know that there is a couple of quite difficult concepts in electromagnetism, but I hope you've enjoyed it because it is one of my favourite topics to teach, and I hope it's one of your favourite topics to learn as well. Thank you for watching. And please remember, if you did like the video, to drop it a like and subscribe to the channel.